and welcome to my talk that's all about scaling up Flux.ml models. My name is Gandhi, and at Flux.ml, we take real great pride in having high quality packages and tools that allow our users to solve modern machine learning problems, be that many billion parameter transformers, tiny scientific machine learning models, or anything in between. We have the flexibility and the capability to not just model these different problems, but also do so in a performant and an efficient and elegant manner. But one place where we feel like we could be improving a lot is in terms of scaling the training of large models. And in this talk, we aim to talk about different strategies that have been developed to help solve this problem, as well as implementations in Julia and Flux, which allow us to not just scale training of Flux models, but in general, many more machine learning packages as well. So let's get started, shall we? So in this talk, I'm going to be talking mostly about two different strategies. One is data parallelism and the other is model parallelism. So these are fairly standard practices, especially the data parallelism, and they have implementations in other packages as well. So it's about time that we had robust data parallelism in Flux too. So how does it actually work? So let's start with a quick rundown of what data parallelism actually is. So let's start by writing what a typical machine learning problem actually looks like. We take a loss, we have a neural network which takes some inputs and we compare it with our outputs over that loss. I'm just going to rewrite this problem to basically be an iteration over every batch in our data set, right? And it's just accumulating the loss as we would naturally do. In ML, obviously, we have to perform many kinds of optimization routines, one of them being SGD or stochastic gradient descent, in which case we have to take gradients against the parameters of our neural network. So let's write that out as well. Notice that in this case, the gradients are in fact linear in our neural network. As you can see, it's just a summation over the entire gradients of the neural network. And our neural network itself is just a collection of different parameters, which means in fact that our gradients are linear in the parameters themselves. So that's a really, really interesting observation because now what we can do is we can rewrite our gradient formula to effectively be a summation or an accumulation over every different parameter over every batch of our data set. And that's a very cool observation because now what we can observe is that we can basically take gradients against different batches and combine them together to basically get gradients against one giant batch of data. So how that's good and all for a theoretical standpoint, but how is it actually practically performed? So let's take a look at that. So we start with our model, which is a standard any model here, any modern machine learning model would work, and then we basically distribute it against different nodes. Effectively, make a copy of that model over multiple GPUs, processors, what have you, and then we start our training process. Now, what does that look like? Our training process effectively involves us taking gradients against mini batches that every individual model copy sees, and then we have to synchronize them. As we saw earlier, uh, we basically need to accumulate the gradients against every parameter, against every batch into one synchronized gradient, which we will then broadcast again back to our copies of models and perform optimization over it. Um, so this is how the nuts and bolts of how a data parallelism model is supposed to look like. So let's see how it works in practice. Here I have set up our package Flux distributed, which effectively performs data parallelism over models that we have written in Flux, and we can take standard models straight out of Metalhead as an example. So let me run a few of these lines, and then I can talk about some of the specifics here. So what we're going to be doing is we're going to be running our uh, data set, which is ImageNet in this case, and we're going to be training a ResNet 34 model over it. So this is a very standard problem, but I wanted to take this opportunity to effectively talk about the different core that we're going to be using, which is Flux distributed. So let me run some of this, and finally we start our training process. Um, so as you can see, we are basically making use of all of the GPUs as we speak. And that's effectively what we expect to see with data parallelism as well. We want to be able to take advantage of all the hardware that we have access to. Now, I wanted to take this opportunity to talk about some of the changes that have happened. So, this is Flux Distributed is the next version of a package that I had previously introduced in one of my previous JuliaCon talks, and there have been a slew of changes since then. And the most major change in that is that we have completely rewritten the internals of Flux Distributed to be way more modular, such that we can actually add in functionality after the fact. So currently it supports very standard uh, data parallel DTP training, but we can easily swap in different strategies as well. For example, if we don't want redundancy in our optimizer states, then we can actually add in a zero optimizer over it as well. Um, Also, earlier iterations used to work over remote channels, which meant that we were paying serialization cost at every training step. This has been completely removed, and we now make use of multiple GPUs over threads, and each one of these GPUs is now able to communicate between each other via P2P and PCIe. And if people have access to more, GPUs that are connected via NVLink, then we can definitely make use of that as well. And in that way, what is basically happening is that we have reduced the amount of latencies that we were seeing earlier to something which allows us to scale up training much more linearly. Um, just to give folks an example, what we're doing right now is we're running our model over 64 batch size for um, each individual GPU, and we have four of those. So effectively, our batch size is 64 times 4. I'm running cycles, which is just the number of mini matches that the model would see, but we could easily replace that with epochs and call it a day. So that's basically how our implementation looks like. And as you can see, it's very simple. But the clever thing to note here, oh, and by the way, this is what the trained model effectively will output, right? So this is the training graph. So you see our accuracy is increasing, our loss decreasing. That's exactly what we expect to see. And one of the clever things here that we're using is we're using datasets.jl. And the major reason for that is so that we can write code that is agnostic to where it is that we are writing and where it is that we're deploying. Another thing is that we're using a custom data loader instead of data loaders.jl because we wanted the flexibility to work with datasets and make it easy to separate loading and pre-processing, which basically means that we now have a custom data loader which allows us to write arbitrary functions that can be interspersed between GPU and CPU operations such that we keep our GPU threads absolutely free. And one example of this, if I can probably show you really quickly, is how we do our batching. So this is just the age top, and notice what happens here. Um, I basically engage all the threads that I have available, but then it sort of quietens down. And the minute I start training is when I see all the activity light up again. And the reason for that is basically that we are interspersing CPU and GPU computation, and we're doing that. I'm sorry, we're overlapping it, and we're doing that such that we don't have to worry about latencies over pre-processing that can happen all on the CPU, and the GPU memory is completely free, and we're ready to basically churn in our data. We maintain an internal buffer such that we don't overwhelm the VRAM, and we always have access to fresh memory to perform our training with. So what are the advantages of data parallelism, right? So one simple one, obvious one is that we are able to work with much larger data sets because we're no longer restricted to just one GPU or one process for that matter. It allows us to increase the batch sizes significantly, which reduces the training times as well. Another thing is that because we're using threads, we are able to make use of linear scaling over our GPUs because we don't have to worry about scheduling things over different processes anymore. which means that our data movement is actually pretty low latency as long as the GPUs themselves are connected via high throughput interconnects. Now, here comes the disadvantages, right? Because these throughput interconnects can be extremely expensive and specialized. And another thing is that in the current implementation, it can become inefficient if we run a multi-process setup, which reduces the amount of parallelism that we have access to, right? Because currently we have been talking about a single node uh, parallelized, parallelized process. But that changes because we have DaggerFlux. Now, what is DaggerFlux? We're basically going to be making use of the same sort of concepts that we have with Flux distributed, but blowing that open to basically involve any differentiable programming model out there. Specifically, we restrict ourselves to working with chain and chain-like objects. Specifically, I mean, if you use Flux, you get a few more niceties, but we have a very general core, which means that any iterable model, be that a Flux chain or a Lux or simple chains model, all of them can fit in just fine. But what is actually happening with model parallelism? So far in data parallelism, what has happened is that we have been restricted in the size of our model still. Why is that? Because we make an inherent assumption that the model can actually fit into a single GPU, which may no longer be the case when we work with many modern transformers, right? That is untenable. So with model parallelism, what we're able to do is we're able to parallelize the model itself, which means that we can break down the model into different layers and those layers as well into sub layers, which each individually can be positioned into separate accelerators and separate processes, separate GPUs, in order to get the most efficient form of that computational graph going. In data parallelism, we have to maintain multiple copies of the model, especially without using zero. It means that we have a lot of redundancy on our optimizer as well. Whereas with model parallelism, we don't have any of these issues. So how is all of this being solved, right? So for points one and two especially, we need out-of-core computation. And the reason for that, again, is that we don't want to be restricted to a single node. And that's where Dagger comes into picture. Dagger is a platform built for out-of-core parallelism, and it has native support for working with GPUs directly. Um, so how does it actually work? I mean, Dagger, as the name suggests, works on this thing called a directed acyclic graph. And as you can see, it's basically a computational graph which goes from one state to the other, and it can have references that skip certain states. It doesn't necessarily need to be linear, but as you can see, it can have branching characteristics. And if you were to compare that to what a typical Flux chain looks like, you have a chain object which has multiple layers in it, and these layers themselves can be self-referential, parallelized, and so on. And basically, the observation that we want to make here is that any program is a DAG, effectively. So how does that actually benefit us? Um, with DaggerFlux, all you really have to do is wrap your model inside this thing called a Dagger chain. And what it does is it takes each one of these layers and converts it into a delayed version of that same layer. What does that actually mean? It means that we're no longer performing computation when we call the model. Instead, what we're doing is we're constructing our computational graph, which we will compute at a later point, having used Dagger's scheduler to parallelize each operation and each layer such that we get the most efficient form of that computational graph out for out-of-core parallelism. So that's good for how the forwards pass works. But let's see how we perform gradients on it, right? Because that's what we ultimately need to do any kind of training of our models. So what does that look like? Typically, what we will do is we'll run a forwards pass, which is our primal, and then the pullback, which is what we'll use to calculate our gradients. Now, in a normal model, that's obviously good, and we're done there. But we no longer have that the case in DaggerFlux. What we have instead is this delayed version of our model, and therefore we pair it with a delayed version of our pullback as well. Now, that's good for one layer, but how do you actually compose this into something more than a single layer network? Um, as we all know, ML model, very typical one, will have a very linear computational graph. Your inputs go to your layer 1, the output goes to layer 2, goes to layer 3, and so on. Now we will want to do the same thing here as well. But the good thing to note here is that our pullbacks actually don't work like that. We actually have to reverse the graph to get sensible gradients out. And this is exactly what we'll do. What we expect to happen is when we introduce our next layer is basically going to construct two separate graphs, one for the primal, the other for the pullback, and we compose them in completely different manners. Ultimately, what this means is that we end up with the observation that parallelization is basically just another form of program transformation. In Flux, especially with Zygote, we're very heavily inspired by compiler program transformation problems, and this is no different. Even though we're not using a compiler directly, and that's because the Dagger scheduler has to work during the runtime, but it nevertheless means that parallelization effectively can be thought of as another program transformation problem. And making that observation means that we are able to take in not just flux models, but any arbitrary chain-like models and actually separate them into their core components and parallelize them over multiple GPUs, processors, what have you. Now, why Dagger? As I mentioned, we could have simply written the graph by hand, but why Dagger specifically? And one of the good reasons for that is that we have to worry about the different computational costs apart from the actual computation itself, one of the major ones being data movement. So anytime we make use of a model, right, we're going to be moving data from one layer to the other, and these layers can live in different parts of our machine. Now, Daggers and Dagger Scheduler is intelligent enough to make intelligent guesses about whether it makes sense for different layers and different operations to live on different machines depending on the latency to access them. And this is very important because it means that we are able to make sure that all the heavy computation does not necessitate us to increase our data movement costs, which can be very expensive. And obviously, this means that this is also highly dependent on the system architecture that we're running on. By that, I don't mean, whether it's a 64-bit or a 32-bit processor, but what I do mean is that, for example, the demo that I showed you had four GPUs in the same machine. That means that the cost to access each one of these GPUs from every other one is relatively low because they're connected via PCIe. And of course, we can have interconnects such as NVLink. But imagine a case where we have four different computers, each connected via an Ethernet port. Now our latencies can be significant, which means that Dagger now has to make the choice to uh, basically coalesce computational components which are very sensitive to data movement latencies together and spread out the rest of them such that we are able to manage our memory properly. So where does this actually come into the picture, right? Where do we see these structures in practice? So here I have a skip connection, and it's actually very common to find these in large neural networks these days. Not just a skip connect. This is an inception, which is a highly branched model. Again, something that would benefit greatly from the kinds of model parallelism opportunities we have. Another example can be a transformer, which itself has submodels, and so on and so on and so on. We have seen these come up in so many domains, and which basically gives us a lot of confidence in saying that this is a very efficient way to make sure that not just are you getting the best sort of performance reference out of any computational model, but also make it such that it's very simple to implement. And we can show that via this very, very short snippet, right? I've taken a resonate out of Metalhead again, and the only thing that I have to do is wrap it in a dagger chain. Now, ResNet is something that obviously makes use of some of these structures as well, which means that when we run our forwards pass, we see that that we get an easy 50% improvement. Granted, this is running on the CPU, but that's just for a demo, right? I mean, this could just as easily have been running on a GPU, and Dagger would have again made use of its scheduler to make great use of where each computational component goes. Notice that in the second example, we have to call collect on our forwards pass, and there's a good reason for that. Um, Dagger by default returns these things called funcs, which are basically delayed computational components, right? And a collect is actually what is going to run that training graph for us. Note that Dagger actually has an eager API, which is something that we are actually observing and exploring. And this might change in the future, but for now, we actually do have to collect on the thunk that DaggerFlux will return. And one of the good reasons for that, again, is that we expect users that have the necessity to parallelize their models, being that computationally a bottleneck, also may be needed to perform delayed computation over a larger graph, right? So if you have to perform a loss at the end of the graph, for example, you would want to make sure that that is accounted for in the scheduler as well. So that's another one of those reasons why we're returning things instead of eager objects. But so this is an example of what we see when we actually run DaggerFlux in action. So this is an example of again running ResNet, and this is a different variant, but this time we're running the backwards pass as well. And the reason we're doing it like this is to basically show how DaggerFlux will scale. Notice how in the end we see a divergence between our baseline implementation as well as DaggerFlux, which basically shows that our computational bounds are extremely well managed with Dagger. Also, it means that we have a very predictable performance profile. Notice how even though the baseline is fairly linear, there are certain ups and downs, whereas Dagger is incredibly linear. So now I have a demo for you guys, which shows DaggerFlux in full force. And the demo that I chose was to train a PDE using a physics-informed neural network. And the reason I'm doing that is I wanted to showcase how flexible DaggerFlux can be. Excuse me. And here we are. So this is an implementation of a very simple 2D PDE. As you can see, I have defined my problem statement using modeling toolkit, and of course I have neural PDE which I will use to actually define my pin. I have to define my boundary conditions and so on. And finally, I have my neural network. So one important observation that I also want to make with this demo is that the actual use case for Dagger in this case is to show of A, the flexibility, but B, that the problem statement itself has to be something that can benefit from the parallelization, especially model parallelization. So here I have my REPL, which is connected to the um, same script. And as you can see, without Dagger chain, my PDE is able to run an iteration over my solve fairly easily. And that should be expected, right? Let's see what happens if I convert my chain into a Dagger chain now. As always, I'm going to wrap my chain into a Dagger chain and then run my model back in again. Notice that this time it's going to be a little bit unfair for us to compare performance, not just because the model itself is fairly simple, but because we're going to be running into a little bit of computational cost. But as you can, sorry, compilation cost. But as you can see, we're able to compose with existing packages just fine. Um, and that was one of the big goals that we had with DaggerFlux too. Not just did we want us to be able to exploit parallelism and basically interplay with as a strategy within Flux distributed, but also make sure that it plays well with problems that are not just standard neural networks or architectures which are well understood in the deep learning domain. All right, with this, we have some next steps. Flux distributed, for example, is already built on a very modular interface, and it basically allows us to switch in different strategies. So we want to implement more of these. In addition, we also have, things like Coco and different kinds of data sets and easy ingestion of these in the pipelines very soon. And another thing is that we want to add a batch parallel version of DaggerFlux inside DaggerFlux so that we can make use of a static model and dynamic data in the same kind of a DAG. Um, and finally, we have identified a bunch of opportunities in Neural PDE to take full advantage of the parallelization available to us. And this is not just for solving pins, but just to make sure that Neural PDE itself can scale with out of core parallelism by itself. We see very promising results already, but moving forward, there's a lot more that we can explore. With this, I want to thank you all. I hope you had somewhat of an informative session, and I would be happy to take any questions. Thank you so much for attending this talk.